A bit array is an array data structure that compactly stores bits. It can be used to implement a simple set data structure. A bit array is effective at exploiting bit-level parallelism in hardware to perform operations quickly. A typical bit array stores kW bits, where W is the number of bits in a unit of storage, such as a byte or word, and K is some non-negative integer. If W does not divide the number of bits to be stored, some space is wasted due to internal fragmentation. Definition: a bit array is a mapping from some domain to values in the set 0, 1. The values can be interpreted as dark, light, absent, present, locked, unlocked, valid, invalid, etc. The point is that there are only two possible values, so they can be stored in one bit. As with other arrays, the access to a single bit can be managed by applying an index to the array. Assuming its size to be n bits, the array can be used to specify a subset of the domain, where a 1-bit indicates the presence and a 0-bit the absence of a number in the set. This set data structure uses about n W words of space, where W is the number of bits in each machine word. Whether the least significant bit or the most significant bit indicates the smallest index number is largely irrelevant, but the former tends to be preferred. Basic operations. Although most machines are not able to address individual bits in memory, nor have instructions to manipulate single bits, each bit in a word can be singled out and manipulated using bitwise operations. In particular, OR can be used to set a bit to 1, 11,101,010 or 0000010 equals 11,101,110, and can be used to set a bit to 0, 11,101,010 and 11,111,101 equals 11,101,000, and together with 0 testing can be used to determine if a bit is set. 11,101,010 and 0000001 equals 0000000 equals 011101010 and 0000010 equals 0000010. XOR can be used to invert or toggle a bit. 11,101,010 XOR 0000010 equals 11101110 11101110 XOR 0000010 equals 11,101,010. NOT can be used to invert all bits. Not 10,110,010 equals 010011101 to obtain a bit mask needed for these operations. We can use a bit shift operator to shift the number 1 to the left by the appropriate number of places, as well as bitwise negation if necessary. Given two bit arrays of the same size representing sets, we can compute their union, intersection, and set theoretic difference using n, w simple bit operations each, as well as the complement of either. For I from 0 to n, w1 complement underscore a I equals not a I union I equals a I or b I intersection I equals a I and b I difference I equals a I, and if we wish to iterate through the bits of a bit array, we can do this efficiently using a doubly nested loop that loops through each word, one at a time. Only n, w memory accesses are required. For I from 0 to n, w1 index equals 0, if needed word equals a I, for b from 0 to w1 value equals word and 10 word equals word shift right 1, do something, with value index equals index plus 1, if needed. Both of these code samples exhibit ideal locality of reference, which will subsequently receive large performance boost from a data cache. If the cache line is k words, only about n weak cache misses will occur. More complex operations. As with character strings, it is straightforward to define length, substring, lexicographical compare, concatenation, reverse operations. The implementation of some of these operations is sensitive to endianness. Population, Hamming weight. If we wish to find the number of 1 bits in a bit array, sometimes called the population count or Hamming weight, there are efficient, branch-free algorithms that can compute the number of bits in a word using a series of simple bit operations. We simply run such an algorithm on each word and keep a running total. Counting zeros is similar. See the Hamming weight article for examples of an efficient implementation. Inversion, vertical flipping of a 1-bit per pixel image, or some FFT algorithms, require to flip the bits of individual words. When this operation is not available on the processor, it's still possible to proceed by successive passes. In this example on 32 bits, exchange two 16-bit half-words, exchange bytes by pairs. Swap bits by pairs, swap bits. The last operation can be written less than 1, greater than 1. Find first one. The find first set or find first one operation identifies the index or position of the 1-bit with the smallest index in an array, and has widespread hardware support and efficient algorithms for its computation. When a priority queue is stored in a bit array, find first one can be used to identify the highest priority element in the queue. To expand a word size find first one to longer arrays, one can find the first non-zero word and then run find first one on that word. The related operations find first zero, count leading zeros, count leading ones, count trailing zeros, count trailing ones, and log base 2 can also be extended to a bit array in a straightforward manner. Compression. A bit array is the densest storage for random bits, that is, where each bit is equally likely to be 0 or 1, and each one is independent. But most data is not random, so it may be possible to store it more compactly. For example, the data of a typical fax image is not random and can be compressed. Run length encoding is commonly used to compress these long streams. However, most compressed data formats are not so easy to access randomly. Also, by compressing bit arrays too aggressively, we run the risk of losing their benefits due to bit-level parallelism. Thus, instead of compressing bit arrays as streams of bits, we might compress them as streams of bytes or words. Advantages and disadvantages. Bit arrays, despite their simplicity, have a number of marked advantages over other data structures for the same problems. They are extremely compact. Few other data structures can store n independent pieces of data in n(w) words. They allow small arrays of bits to be stored and manipulated in the register set for long periods of time with no memory accesses. Because of their ability to exploit bit-level parallelism, limit memory access, and maximally use the data cache, they often outperform many other data structures on practical datasets, even those that are more asymptotically efficient. However, bit arrays aren't the solution to everything. In particular, without compression, they are wasteful set data structures for sparse sets in both time and space. For such applications, compressed bit arrays, Judy arrays, tries, or even Bloom filters should be considered instead. Accessing individual elements can be expensive and difficult to express in some languages. If random access is more common than sequential and the array is relatively small, a byte array may be preferable on a machine with byte addressing. A word array, however, is probably not justified due to the huge space overhead and additional cache misses it causes, unless the machine only has word addressing. Applications. Because of their compactness, bit arrays have a number of applications in areas where space or efficiency is at a premium. Most commonly, they are used to represent a simple group of Boolean flags or an ordered sequence of Boolean values. Bit arrays are used for priority queues, where the bit at index k is set if and only if k is in the queue. This data structure is used, for example, by the Linux kernel, and benefits strongly from a find first zero operation in hardware. Bit arrays can be used for the allocation of memory pages, inodes, disk sectors, etc. In such cases, the term bitmap may be used. However, this term is frequently used to refer to raster images, which may use multiple bits per pixel. Another application of bit arrays is the Bloom filter, a probabilistic set data structure that can store large sets in a small space in exchange for a small probability of error. It is also possible to build probabilistic hash tables based on bit arrays that accept either false positives or false negatives. Bit arrays and the operations on them are also important for constructing succinct data structures, which use close to the minimum possible space. In this context, operations like finding the nth 1 bit or counting the number of 1 bits up to a certain position become important. Bit arrays are also a useful abstraction for examining streams of compressed data, which often contain elements that occupy portions of bytes or are not byte-aligned. For example, the compressed Huffman coding representation of a single 8-bit character can be anywhere from 1 to 255 bits long. In information retrieval, bit arrays are a good representation for the posting lists of very frequent terms. If we compute the gaps between adjacent values in a list of strictly increasing integers and encode them using unary coding, the result is a bit array with a 1 bit in the nth position if and only if n is in the list. The implied probability of a gap of n is 1/2 n. This is also the special case of Go-lump coding where the parameter m is 1. This parameter is only normally selected when log 1, or roughly the term occurs in at least 38% of documents. Language support. The C programming language's bit fields, pseudo-objects found in structs with size equal to some number of bits, are in fact small bit arrays. They are limited in that they cannot span words. Although they give a convenient syntax, the bits are still accessed using bitwise operators on most machines, and they can only be defined statically. It is also a common idiom for C programmers to use words as small bit arrays and access bits of them using bit operators. A widely available header file included in the X11 system, extrapbits, H, is a portable way for systems to define bit field manipulation of arrays of bits. A more explanatory description of aforementioned approach can be found in the comp.lang.c fac. In C++, although individual bools typically occupy the same space as a byte or an integer, the STL type vector less than bool greater than is a partial template specialization in which bits are packed as a space efficiency optimization. Since bytes are the smallest addressable unit in C++, the operator does not return a reference to an element, but instead returns a proxy reference. This might seem a minor point, but it means that vector less than bool greater than is not a standard STL container, which is why the use of vector less than bool greater than is generally discouraged. Another unique STL class, bitset, creates a vector of bits fixed at a particular size at compile time, and in its interface and syntax more resembles the idiomatic use of words as bit sets by C programmers. It also has some additional power, such as the ability to efficiently count the number of bits that are set. The Boost C++ libraries provide a dynamic _bitset class whose size is specified at runtime. The D programming language provides bit arrays in its standard library Phobos in std.bitmanip. As in C++, the operator does not return a reference, since individual bits are not directly addressable on most hardware, but instead returns a bool. In Java, the class bitset creates a bit array that is then manipulated with functions named after bitwise operators familiar to C programmers. Unlike the bitset in C++, the Java bitset does not have a size state. A bit can be set or tested at any index. In addition, there is a class enumset, which represents a set of values of an enumerated type internally as a bit vector, as a safer alternative to bit fields. The .NET framework supplies a bit array collection class. It stores Boolean values, supports random access and bitwise operators, can be iterated over, and its length property can be changed to grow or truncate it. Although Standard ML has no support for bit arrays, Standard ML of New Jersey has an extension, the bit array structure, in its SML/NJ library. It is not fixed in size and supports set operations and bit operations, including, unusually, shift operations. Haskell likewise currently lacks standard support for bitwise operations, but both GHC and Hugs provide a data bits module with assorted bitwise functions and operators, including shift and rotate operations, and an unbox array over Boolean values and may be used to model a bit array, although this lacks support from the former module. In Perl, strings can be used as expandable bit arrays. They can be manipulated using the usual bitwise operators, and individual bits can be tested and set using the VEC function. In Ruby, you can access a bit of an integer using the bracket operator, as if it were an array of bits. Apple's core foundation library contains CF bitvector and CF mutable bitvector structures. Place.I supports arrays of bit strings of arbitrary length, which may be either fixed length or varying. The array elements may be aligned. Each element begins on a byte or word boundary, or unaligned. Elements immediately follow each other with no padding. Hardware description languages such as VHDL, Verilog, and System Verilog natively support bit vectors, as these are used to model storage elements like flip-flops, hardware buses, and hardware signals in general. In hardware verification languages such as OpenVara and System Verilog, bit vectors are used to sample values from the hardware models, and to represent data that is transferred to hardware during simulations.